we're standardizing our sodium hydroxide aqueous solution. In other words, just figuring out the concentration with accuracy and precision. We're going to do this via titration against a oxalic acid standard solution. And so we're going to have a Florence flask, a 250 milliliter Florence flask filled with oxalic acid. This oxalic acid, we know to what, or how many sig figs? 5 sig figs. And so this is a 5 sig fig concentration. If I add drops of water to this, then that's going to screw it up. And so I don't want to do that. And so this is my oxalic acid standard. Now, what I need to do is I need to transfer 25 milliliters of this oxalic acid standard into an Erlenmeyer flask. Not just 25, I want to get 25.00 milliliters of oxalic acid standard. And so I'm going to have to use volumetric glassware. In this case, you know, I could use a 50 milliliter grad cylinder or 25 milliliter grad cylinder, but I'm not. You know, what would be easier to use is a 25 milliliter pipette. And so if I use a 25 milliliter pipette, should I stick the pipette straight into this? No, because then I risk contaminating this solution. I don't want to contaminate. So what I'm going to do is I'm going to transfer some into a beaker. Now when I transfer it into a beaker, I need to make sure the beaker has been cleaned. Beakers are easy to dry, so I could either dry it or I could give it a final rinse with oxalic acid standard. But what I don't want to do is I don't want to contaminate it with water. And so I'll transfer some of this solution into a beaker. Probably better to get a narrower, taller beaker than a wider, shorter beaker, because it's just easier to pull solution if it's taller. We run less risk of sucking air into our 25 milliliter pipette. And so this will be a 25 milliliter pipette. A 25 milliliter pipette doesn't measure 25 milliliters of water. How much water does it measure out? It measures out 25.00 milliliters. Volumetric glassware is good to the nearest hundredth of a milliliter. And so I'll transfer a little bit over here, make sure that this is either dry or been given a final rinse with oxalic acid, and then I'll pipette it into here, into my flask. All right, does this Erlenmeyer flask need to be dry? Does it need to be dry? Actually, no, it doesn't need to be dry. Should I give it a final rinse with oxalic acid standard? Should I rinse some? Use some of this 25 milliliters to rinse this out? No. In fact, this Erlenmeyer flask can be wet. This one need not be dry. So this beaker needs to be dry. But once I get my portion, then this could be wet, because I'm going to have 25 milliliters here, and then I'm going to add water. How many mils of water will I add to this? I think it says add another 25 milliliters. Is that correct? Add water. And phenolphthalein. Well, isn't adding water and phenolphthalein going to screw up the concentration? It is, but we are no longer measuring the volume. And so what we know here is we have a fixed number of moles. Adding water and phenolphthalein is not going to change the number of moles of acid in here. And then what we'll do is we're going to titrate this against our sodium hydroxide. And so in the burette, this will be a burette, we're going to place our sodium hydroxide solution in here. Now the burette has to be cleaned. The burette's too difficult to dry, so we aren't going to dry it. So does the burette have to be rinsed with sodium hydroxide solution as a final rinse, or can it be rinsed with water, DI water, as the final rinse? No, it has to be sodium hydroxide solution. Otherwise, if there's water in here, that's going to change the concentration, and it's going to change the concentration different amounts depending on how much water was in there. And it's only to part of our sodium hydroxide. We have 500 milliliters of sodium hydroxide. And we got to keep it all at the same concentration. So this has got to be rinsed with a final rinse of sodium hydroxide solution. And then we titrate it. We're going to titrate it to the nearest half a drop. And then we should be able to get the molarity of the sodium hydroxide. The molarity of the sodium hydroxide is going to equal the moles of sodium hydroxide divided by the liters. The liters of sodium hydroxide, this is going to come from the volume of titrant here. The volume of titrant, which is the volume of sodium hydroxide, is going to be in milliliters. And then we convert that to liters. And then we use that here. This is going to be liters of sodium hydroxide used to react with oxalic acid. Well, how much is that? Well, we just record it off the burette. Now, the moles of sodium hydroxide we're going to get from this. We know how many moles of acid we have. How do we know how many moles of acid? Because we know how many milliliters of oxalic acid standard we use. And so the milliliters of oxalic acid standard can be converted, actually I'm just do it this way, can be converted into liters, which can be converted into moles of oxalic acid standard. The moles of oxalic acid standard, this comes from earlier calculation. The earlier calculation was, how many grams we used, converted into moles of dihydrate, converted into moles of oxalic acid divided by 0.250. And so this is from earlier. And that is the molarity of our oxalic acid standard. Once we have the moles of oxalic acid standard, then we can get the moles of sodium hydroxide from the balanced chemical equation. The balanced chemical equation is going to come like this. Oxalic acid is a diprotic acid. That means both of these hydrogens are acidic. And that means it's going to take 2 sodium hydroxides to neutralize 1 oxalic acid. That's going to form sodium oxalate and 2 waters. And so the mole ratios is 2-to-1 mole ratio. That is 2 moles of sodium hydroxide for every 1 mole of oxalic acid. And so that gives us moles of sodium hydroxide. If we take our moles of sodium hydroxide and divide it by the volume of sodium hydroxide in liters, that will give us our molarity. And so we do one run, but we have to worry about random error. Random error is these just fluctuations in reading. And so what we're going to do is we're going to do at least 3 runs, a minimum of 3 runs. These 3 runs must have a precision, an absolute precision of less than 0.5%. What that means is this. That means you take the biggest concentration, let's say run 2 gave you the biggest, minus the smallest concentration, let's say run 1 or 3 gave you the smallest, divided by the smallest times 100%. And so just find out of those 3 which one's the biggest, which one's the smallest, and do this calculation. This has to be less than 5%. If it comes out greater than 5%, then you have to do another run. Then must do another run. If we do a run 4, then we'll have 4 runs. If we have 4 runs, then we look at each run. Run 1, run 2, run 3, run 4. And then what you're going to do is you're going to pick the closest 3. And recalculate. Biggest minus smallest divided by the smallest. If it's less than 5%, then we're going to average those 3. If it's greater than 5%, then you're going to do another run. And you're going to keep doing runs until you can find 3 that are close. But you have to be careful because some people, they're on run 8, run 9, and then do you know what happened? They ran out of sodium hydroxide. If you run out of sodium hydroxide, what do you have to do? Start the whole thing over again. This is a lot of work. And so if your precision is bad, it could be, could be something that you should correct. So for example, one of the reasons that people had bad precision like that, the person who had 8 runs, is because they didn't know how to read the burette properly. They kept misreading the burette, and therefore their runs were all over the place. And so, if you need a little refresher on how to read the burette, come talk to me. Another reason that people had poor precision is there was an air bubble in the tip. Air is pretty compressible. So sometimes the air was compressed and the volume was a little lower. Sometimes the air expanded and the volume was a little greater. And so there are little fluctuations there based on that little air pocket there. And so if you're finding your precision to be poor, this is 0.5%. 5% is pretty easy. 0.5% is more difficult. If you're finding your precision poor, then think about your technique. Maybe your technique isn't good and needs improvement. All right, so you might have to do run 5. If you do run 5, pick the best 3. Run 6, pick the best 3. Okay, once you're done with this, then what we're going to do is we're going to average the best 3 runs to get the molarity of sodium hydroxide. This is going to be standard. And it's just going to be the average of the best 3. Okay, this molarity should be known to how many sig figs. So when I look at this, this is 4 sig figs. We should be able to get 4 sig figs out of this here. And therefore, we're going to call it a standard solution. It should be accurate and it should be precise. Now, once we've standardized the sodium hydroxide, we're going to go to part 2. What we're doing in part 2 is this. Part 2 is going to be the determination of the molar mass of an unknown acid. All right, the molar mass of the unknown acid. Let me tell you, the acid is not totally unknown. The acid is going to be a solid organic acid, like oxalic acid. Oxalic acid is white solid. It's a carboxylic acid. Citric acid is a white solid. It's an organic acid. And so, in order to get the molar mass, we need to know the mass of the acid. And so the mass of the unknown acid is easy. Just weigh it on a balance. Weigh on balance. But how many grams do you need? Well, the number of grams that you need will be written on the vial. And so your vial might say 0.2 grams. That means get 0.2 grams. But get it to how many sig figs?
5.
Yeah, 4 or 5 sig figs. Weigh on balance to 4 to 5 sig figs. And then we need the moles of acid. The moles of acid we're going to get via titration. But in this case, we're going to titrate our unknown acid with the sodium hydroxide standard solution. And so the mass of acid is easy. We'll just weigh it. And that many grams of acid we're going to titrate here. And so what we're going to do is we're going to weigh a sample of acid into a beaker like this, dissolve it with water, and then transfer it into a Erlenmeyer flask completely. And then titrate using the sodium hydroxide in a burette. When we do that, then we're going to get the milliliters of sodium hydroxide required for titration. From milliliters of sodium hydroxide, we'll go to liters. from liters of sodium hydroxide, we'll go to moles of sodium hydroxide, because now we know the molarity to 4 sig figs. This would be the molarity that we determined in part 1. From the moles of sodium hydroxide, we could go to the moles of acid. But this cannot be a totally unknown acid. Something has to be known about this acid. And what has to be given is this. And it's given on the vial. Whether the acid is monoprotic or diprotic. That is the acid an HA, monoprotic, where A is a generic anion, or H2A? And so that's going to change the conversion factor. If it's monoprotic, then it's a 1-to-1 mole ratio. 1 mole of acid, unknown acid, for every 1 mole of sodium hydroxide. If it's a diprotic acid, then it gets a different mole ratio. If it's diprotic acid, it's 1 mole of acid for every 2 moles of sodium hydroxide. This would be like oxalic acid. But it doesn't have to be oxalic acid. There are other diprotic acids out there. And so it's not a total unknown. Otherwise, we wouldn't be able to figure this out. We don't know if it's a monoprotic acid or diprotic acid. We have to be told what it is. Okay, again, with this part, we're going to do 3 runs or 3 trials with 1% precision. And so you have a little bit more leeway here. But that means you have to keep going until you get 3 good runs with less than 1% precision. Okay. All right, are there any questions on this? So today, what are we going to do? Today, we're going to mix up our oxalic acid standard solution and our sodium hydroxide solution. Okay, to avoid a crunch at the balances, we'll divide the room in half. So maybe this half will go and make the oxalic acid, and the other half will make the sodium hydroxide first. Sodium hydroxide's there, the oxalic acid you get from the stockroom, along with your volumetric flask here. Okay. Goggles are required for this. If you forgot your goggles, I have some extras here.